All right. Let's go. Let me check Zoom one more time. Okay. Let's see if this still works. Nope. All right. So greetings, scholars. Let me see. No real announcements other than midterm grades are available. So you should be able to see the details of how I calculated the midterm grades on Blackboard. Basically, I calculated our grades like normal. So I took your exam average and scaled it to 80% of our grade. And then your homework was 10% and your quizzes were 10%. So then I got a score. That score served as 90% of your overall grade. And then the other 10% came for whatever grade Dr. Lamar provided for each of you. So then her grade combined with mine made up the midterm grade. So again, you can see those details on Blackboard, and then, the official midterm grade is there, it's posted. Keep in mind that the midterm grade is just a snapshot of where you are at this moment in time. It has no bearing on your final grade. So you can just use that as a gauge. If your grade is lower than you would like, then you have to make some kind of adjustment, do something different to get a different outcome. And then if your grade is closer to where you'd like, then then it's a matter of trying to maintain through the end. We don't have that many topics remaining, right? So in chapter 2, we only have 3 sections: 2.1, 2.2, and 2.3. So today we're going to be working on section 2.2, polynomial functions. And then next week is 2.3, and then the week after that is exam 3, right? And then after that, we only have 2 sections remaining. I think it's like 3.1 and 6.4, and then we have our Thanksgiving holiday, and then from there we're just like reviewing for the final, right? Yeah, so it's not that many topics, and maybe it's like a solid month of material left, a little over a month. As usual, if you have questions, feel free to unmute yourself to get my attention, or type in the chat and we can talk about it. Otherwise, we're going to go through as much of this section together today as we can. Sorry. This is a long section, so we're not going to be able to get through all of this together. Again, we'll make it as far as we can, but whatever we don't finish, I hate to say together again because I said it like 12 times already, but whatever we don't finish together, I do expect you to use my pre-recorded lecture to finish out. This is definitely one where you want to see the whole presentation, and anything that I would say in the pre-recorded lecture is the exact same thing I would say live, right? And then more than likely on Wednesday, we'll go through as many homework questions from this section together as we can. Okay, there's the word together again. Okay, so section 2.2 is on polynomial functions. And a few objectives: 1, learn properties of the graphs of polynomial functions. 2, determine the end behavior of polynomial functions. 3, find the zeros of a polynomial function by factoring. 4, identify the relationship between degrees, real zeros, and turning points. 5, graph polynomial functions. A polynomial function of degree n is a function of this form, where n is a non-negative integer and the coefficients an minus 1, an minus 2, a2, a1, a0. These are real numbers where the an is not equal to 0. So the leading coefficient is not 0. I like to describe polynomial functions as a finite sum of monomials, right? So then what is a monomial? A monomial is a term where you have a real coefficient times some variable raised to a non-negative integer power. So then once you are clear about what a monomial is, then a polynomial is just the finite sum of monomials. Let me see something here. Oh, I think we're still good. So let me mark these other gentlemen that's absent. I really like taking attendance in Blackboard. It's just so smooth and effortless. Okay, oh, shoot. Okay. So the term a n x to the n is called the leading term. The number a sub n is called the leading coefficient, and a naught is the constant term. A constant function f of x equals a, where a is not equal to 0, which may be written as the form f of x equals a times x to the power of 0, is a polynomial of degree 0, right? So if we have f of x equals some constant other than 0, some non-zero constant, like f of x equals 2, f of x equals 7, or f of x equals 13, or a million, or whatever, we say this is a polynomial of degree 0 because it can be rewritten as that number times x to the power of 0. Keep in mind, x to the power of 0 is 1. 1 times anything is itself, right? The 0 function, f of x equal to 0, has no degree assigned to it because it's not unique, right? Like f of x equal to 0 is the same as 0 times x squared, which is the same as 0 times x to the 5. You can keep writing that x with, any power that you want. They all collapse to 0. All right, so because the degree is not unique, we said the 0 function has no degree assigned to it. Polynomials of degree 3, 4, and 5 are called cubic, quartic, and quintic polynomials. So let me see, this expression that you see here, we call this a polynomial function. Again, a finite sum of monomials. The function, somebody have a question? The function f, defined by f of x equal to this expression, is called a polynomial function. And this equation where we have the polynomial equal to 0, we call that a polynomial equation. Okay. So a few common properties of polynomial functions. 1, the domain of a polynomial function is a set of all real numbers. 2, the graph of a polynomial function is a continuous curve, right? There are no holes or gaps or breaks. So for instance, if we look at the image on the left, we can pick any point, right? And we can start to trace the graph in either direction. And we can get to any other point without picking our pencil up, right? But if we started with the graph on the right, say we started here, and we start tracing, in order to get to the other side, we have to pick our pencil up, in order to pick it up. Because there's a hole or a gap or a break, the graph on the right cannot be the graph of a polynomial, right? So again, the graph of a polynomial function is a continuous curve, as on the left. The graph on the right cannot be the graph of a polynomial because we have a hole or a gap or a break because of this guy here, okay? So then the third property for polynomial functions is that the graph of a polynomial function is a smooth curve. Notice all these curves are smooth, all right? Smooth curve, smooth curve, smooth curve, right? The graph on the right cannot be the graph of a polynomial because we have these sharp corners. Here's another sharp corner and another one. So because of those sharp edges, that cannot be the graph of a polynomial. So to kind of recap, 3 properties of polynomials: their domain is all reals, the graph of a polynomial function is continuous, and and also a smooth curve, right? So even though the graph on the right is continuous, but it's not a smooth curve, so it cannot be the graph of a polynomial. So here we're asked to state which functions are polynomial functions. For each polynomial function, find its degree, the leading term, and the leading coefficient. Okay. Notice that for A, we have a finite sum of monomials, right? We call this a trinomial because it's the sum of 3 monomials, where there are 3 terms, 3 things that are being added together. Okay. So this one is yes, it's a polynomial. Let's see. find the degree. So the degree of a polynomial is the highest power on any variable. So the degree here is going to be 4. Okay. The leading term is the term with the highest degree. So our leading term is going to be 5x to the 4. And our leading coefficient is going to be the constant term on the leading term, which is going to be 5 in this case. Okay. So hopefully we're all aboard and not all bored. I know, this hour is always tough for me. I don't know if it's tough for you, but it's definitely tough for me because I'm like, this is like prime nap time. It's nap time. Gotta go to sleep, right? Man, I tell you, the naps at this hour just be like the best. But that also happens because I'm usually up like all night, like every night. So that's why it's like I can't, I'm not doing a 9 to 5. It seems like a nightmare to me because I'll be up every night, no alarm clock, just up. So that's when I get most of my work done, is in the middle of the night. If we look at this part B, now if we were only looking at this expression, it would be a polynomial, right? It's a finite sum of monomials. But because the domain is not all reals, then it cannot be the graph of a polynomial. Give me just a moment. Trying to wait till I got out of class here. You can have this. Oh. Let's see. It's spicy, so be careful. It's like she knows when I'm about to share food with her. I was trying to pretend like I wasn't gonna share it with her. She's just like, frantic, like, oh my God, can I please have some? Like focused. All right, okay, let's go on to the next one. Yeah. So the power function. A function of this form, f of x equals a times x to the n, is called a power function of degree n, where a is a non-zero real number and n is a positive integer. So if we consider the power function, if n is even, right? So if we take a negative number raised to an even power, then the negative goes away and it becomes positive, right? So if we consider f of negative x, right, we replace each x with negative x, we get a times negative x to the n, but n is even, so then that's going to be the same as a times x to the n, which is the original, right? So again, we started with f of negative x and we finished with the original. That's the definition of a function being even. All right, let me say that one more time. When we evaluate f of negative x and we get back to the original, that's the definition of a function being even. Once we identify a function as even, that's the same as it having y-axis symmetry, right? Y-axis symmetry, if you look at the graph, the y-axis is going to cut it in half. If you fold it along the y-axis, the left hand matches the right hand. Another way to articulate y-axis symmetry, whenever we have the point x comma y, we also have the point negative x comma y, right? So you get a point on one side, you automatically get a point on the other. Okay. So if we have a definition for a function being even, then it stands to reason that, well, maybe we have a definition of a function being odd, right? So if we consider the power function, and if n is odd, then when we evaluate negative x to the n, an odd number of negatives multiplied is going to be negative. So this is the same as negative x to the n. So then when we evaluate f of negative x, ultimately we're going to finish with a negative times f of x. That's the definition of a function being odd. Let's say that one more time. When we evaluate f of negative x and we finish with a negative times the original, that's the definition of a function being odd. Okay. Once we identify a function being odd, that's the same as the function having origin symmetry, or symmetry with respect to the origin. Origin symmetry is like if you have an image with origin symmetry, if you cut the image along the x-axis, you put your thumb on the origin and rotate it 180 degrees, the top half is going to match the bottom half. Another way to articulate origin symmetry, whenever we have the point x comma y, we also have the point negative x comma negative y. All right, so all the points are equidistant and symmetric about the origin. They're kind of like dancing around the origin or whatever. Okay, so a quick recap. Whenever we evaluate f of negative x and we get back to the original, that's the definition of a function being even. And when we evaluate f of negative x and we get a negative times the original, that's the definition of a function being odd. Even means y-axis symmetry, odd means origin symmetry. Let me check. Zoom. Okay. Okay. So then next, we have these 4 cases for end behavior of polynomial functions. And so these first 4 cases are kind of like focused on the power function. So power function, and let me see, can I paste, is it still saved? No. Okay. So in these first 2 cases, we're going to look at where n is even. N is going to be the degree of our power function. So when the degree of the power function is even, then, let's see. So in this case 1, our leading coefficient is positive and our n is even. When our leading coefficient is positive, that means our graph goes up to the right. The leading coefficient tells us about the right-hand behavior of the graph. So a positive leading coefficient means our graph goes up to the right. When the degree of our polynomial is even, that means the other side does the exact same. Even means exact same, right? So a positive leading coefficient means we go up to the right. Even meaning the exact same, so that means we're going to go up to the left, all right? That's what you see here. In the next case, our leading coefficient is going to be negative, and our n is even. So if our leading coefficient is negative, then that means what? Our graph falls to the right. Even means the exact same, so it's also going to fall to the left. You see it? I don't know. We see it here. Paste. A negative leading coefficient means our graph falls to the right. N being even means the other side does the exact same, so it's going to fall to the left. Okay, so we saw 2 cases where n is even. The next 2 cases is where n is odd. So now we're back to a positive leading coefficient. So a positive leading coefficient means what? The graph goes up to the right. N is odd means the other side does the opposite. So odd means opposite. So if our n is odd, then the other side does the opposite. So if we go up to the right, that means we're going to go down to the left, right? So a positive leading coefficient up to the right, our n is odd, paste. N is odd means we go down, the other side does the opposite, which is down to the left. Okay. And then finally, when our leading coefficient is negative, we're going to go down to the right. N is odd means the other side does the opposite, so we're going to go up to the left, down to the right and up to the left. So we saw these four cases for the power function and how the leading coefficient in conjunction with the degree of the polynomial tells us about how the graph behaves as x tends to positive infinity or negative infinity. The sign of the leading coefficient tells us how the graph behaves as x tends to infinity. The degree of the polynomial being even or odd tells us about how the graph behaves as x tends to negative infinity. Okay. So we saw these four cases for the power function. So then if we consider this polynomial of degree 3, we want to show that this polynomial is approximately equal to 2x to the power of 3 when the absolute value of x is very large. Okay. Okay. So let's start with the copy of our polynomial. 2x cubed plus 5x squared minus 7x plus 11. Okay. So next, let's factor out x cubed from all the terms. We're going to be left with 2 plus 5 over x minus 7 over x squared plus 11 over x cubed. And then if we consider this as the absolute value of x tends to positive infinity, what happens to these terms, right? If we think about 5 divided by x, like when x is 1, 5 divided by 1, you get an answer. 5 divided by 5, you get an answer. 5 divided by 10, you get an answer. Divided by 20, divided by 50, divided by 100, divided by 500, right? So as that denominator gets bigger and bigger and bigger, you should notice that this term gets closer and closer and closer, or smaller and smaller and smaller, is closer to what? 0. Same thing for this guy. As that denominator gets bigger and bigger and bigger, this tends to 0, and this tends to 0. So as x goes off to positive infinity, then this guy is going to be approximately equal to, just be a little bit OCD here. I just realized I canceled out my I think all that's left is the 2x cubed, right? So as the absolute value of x gets large, then our original polynomial behaves more and more like this power function. And we know that for this power function, because the leading coefficient is positive, it's going to go up to the right. Because the degree of the polynomial is odd, the other side is going to do the opposite, so it's going to go down to the left. This doesn't give us any information about the middle, but you know. Just copy. I just realized because what I did, I canceled copy paste. Okay. Okay. So then that brings us to the leading term test. So let f of x be this polynomial function where the leading coefficient is not 0, be a polynomial function. Its leading term is a(n) x to n. The behavior of the graph f as x tends to infinity or negative infinity is similar to one of the following four graphs and is described as shown in each case. The middle portion of each graph indicated by the dashed lines is not determined by the test, right? So this is going to parallel those four cases that we saw just a moment ago. Let me paste. Let's delete this one. So in this case, a positive leading coefficient and our n is even. A positive leading coefficient, our graph should go up to the right. Even means the exact same. So the other side is the exact same thing. So it should go up to the left. So up to the right, up to the left. A negative leading coefficient down to the right. N being even means the exact same. So it should go down to the left. Down to the right, down to the left. Paste. This is even. Okay. And then we consider the two cases when n is odd. positive leading coefficient is going to go up to the right. Odd means opposite, so it's going to go down to the left. And then when our leading coefficient is negative, it's going to go down to the right, and odd means opposite, so the other side's going to do the opposite, so it's going to go up to the left. Down to the right and up to the left. Okay. So hopefully we're all aboard and we're not all aboard. If you have questions, again, don't hesitate to unmute yourself or type in the chat. Get my attention and we can talk about it. Okay, let's keep going. So, okay. So here we're actually using the leading term test to determine the end behavior of this graph. So all we need to do is look at identify the leading term. Notice that the leading coefficient is negative, right? A negative leading coefficient means our graph is going to fall to the right. And then the degree of the polynomial being 3, which is odd, means the other side is going to do the opposite, so it's going to go up to the left. What is so important? I know there's nothing out there. You see, huh? You see some squirrels? I'm sorry. What? What is it? Huh? What? Is it a bird? Is it a squirrel? Or does yard need some attention? I'm about to let you out. Just give me like 10 minutes. Can I get like 10 minutes? Yeah. Where are you bringing your snacks out here? Okay. All right. So what we're doing is like building a case on some different graphing techniques, right? And so when we're working with polynomials, we can use the leading term to get a sense of what happens as x tends to positive infinity or negative infinity. What this one is saying is that as x tends to positive infinity, y goes to negative infinity. And then as x tends to negative infinity, y goes to positive infinity, right? That's all that this is telling us. Oh, and then these are typos. Those R's are supposed to be right arrows. So for instance, this is supposed to be y tends to positive infinity as x tends to negative infinity. And y tends to negative infinity as x tends to positive. Right, that's another way of saying what I drew in with those symbols. This little, symbolic form is articulated like this, which you see in red. Okay. So then we have real zeros of polynomial functions. If f is a polynomial function and c is a real number, then the following statements are equivalent. 1, c is a zero of f. 2, c is a solution or root of the equation f of x equals 0. 3, c is an x-intercept of the graph of f. The point c, 0 is on the graph of f. For some reason, I just have this urge to say 4, but there's no 4, right? The way I was reading it with the inflection and intonation, I felt like I should have said 4, but there was no 4. But the main takeaway here is that these three phrases can be used interchangeably. So whenever you hear me say, like, talking about the x-intercept, that's the same as saying find the solution of the equation f of x equals 0, find the solution of root. But then that's the same as saying find the 0 of the function, right? So all three of these phrases / concepts can be used interchangeably. My dog is so antsy. She's like, get me out of here. I need to take her for a walk. Let's see. So here we're asked to find the zeros of each polynomial. Let me select this, duplicate. Yep, that works. So now you're not going to work. I bet you're not working. Oh, you are working. Okay, thank you. Okay. So let's work on part A. Okay, so for part A, find the zeros. So we're going to take this f of x equal to x to the 4 minus 2x cubed minus 3x squared equal to 0, all right? Basically, what we have to do to solve this equation, this polynomial equation, we have to use factoring. So as a disclaimer, for this course, we do expect you to already know factoring, but that's why we have things like the lab component to kind of strengthen that area. If you need additional attention specifically on factoring, if we open up, if we go into our Blackboard module or whatever, and we access it like we're accessing the notes. Near the notes, you're going to find a folder that says handouts, right? I think I shared there. You're going to find a folder that says handouts. In that folder, you're going to see at least 2 handouts devoted to factoring. One handout is a 1-page document that summarizes how to approach a factoring problem. So it's like the questions we should ask ourselves whenever we're trying to factor something. And then the other document is an entire chapter devoted to factoring. And so basically what it does is give it kind of explains the different scenarios and gives practice for all the different for at least 90% or higher of the different factoring scenarios that we'll come across in this course. And so basically what it is, I pulled a scan from another text and I saved it because it's devoted specifically to factoring. So anybody that wants to practice on factoring, that's already available on our Blackboard page. Access it that box folder link, like you're accessing the notes. You're going to see a folder that says handouts, and that's where it is. Okay. So here we have a trinomial because we have 3 terms. If we're going to go factor, the first question that we're going to ask ourselves, is there a greatest common factor? And we would say, yeah, all the terms have something in common that we can factor out. It looks like we can factor out with x squared from every term. So if we factor out an x squared, we're going to be left with x squared minus 2x minus 3 equals 0. Okay. So then we want to take this further. And can we factor it to a form like this? Now, because this second sign is negative, I know my signs are opposite. One has to be positive and one has to be negative. Because the first sign is negative, that tells me the larger number is negative. So we're looking for 2 numbers that multiply to give us -3 and add to give us -2. So it's -3 and 1. So then in this form, when 2 or more factors, when two or more things multiply to give us 0, we set each factor to 0 and solve. So we're going to have x squared equals 0, or x plus 1 equals 0, or x minus 3 equals 0. Okay. Here we get x equals 0, or x equals -1, or x equals 3. Okay. So then when we plug any of these into the original, they should all make the original 0. Then for part B, so we're working with g of x equal to x cubed minus 2x squared plus x minus 2. We're going to set this equal to 0 and solve. So this is a special factoring case because we have 4 or more terms. We're going to use a technique called factor by grouping. So I'm putting this green bar because I want to consider the first 2 by themselves and then the second 2 by themselves. We try one grouping, see if we can factor it. If not, we rearrange it and regroup it and then try again, right? So if we consider the first 2 terms, do they have a greatest common factor? Yeah. We can factor out x squared from each of those terms. And we're going to be left with x minus 2. The hint is we're looking for x minus 2 on the right, and we got lucky because it's already there. We bring down our plus, right? So then what we want to do is those blue parts are called a common binomial factor. All right, so we want to factor out this common binomial factor. Okay, so if we move the blues to the front, then we're going to be left with x squared plus 1 equal to 0. Okay, so then we use the zero factor property. We have two or more things that multiply to give us 0. So then we say x minus 2 equals 0, or x squared plus 1 equals 0. From the first one, we get x equals 2. Thank you. From the second one, if we try to solve, if we subtract 1 and take the square root, we're going to be taking the square root of a negative. So that one has no real solution or no solution. But the only 0 we get from part B is x equals 2. Again, we should plug it into the original to check, make sure that it works. Most classes I stopped here. Okay. At least one of my classes. I'm going to go ahead and kind of introduce this next concept, and then we'll close out. So then we have the intermediate value theorem. Let A and B be two numbers such that A is less than B. If f is a polynomial function such that f of A and f of B have opposite signs, then there is at least one number C with C being between A and B for which f of C equals 0, right? So this is so the intermediate value theorem is piggybacking off the notion that polynomial functions are continuous, no holes or gaps or breaks. So if we consider two different x values where A is strictly less than B, and f of A and f of B have opposite signs, that means somewhere between those x values, our function has to cross the x-axis in order to change signs, right? So we have a pictorial representation here. So notice our f of A is positive, our f of B is negative. So there's a C between, here's our A, and here's our B, right? So there's a C between A and B such that f of C equals 0. Same thing here. F of A is negative, f of B is positive. There's a C between A and B. Here's A, here's B. So there has to be a C between A and B such that f of C equals 0. And then this is saying that we're guaranteed at least 1 0. Working a polynomial, f of A is positive, f of B is negative. We have at least one. Now in this case we had 3, but we have at least 1 0 between those guys. Okay. So this is as far as I made it with at least one of my other classes. So we're actually going to stop here. Are there any burning questions for me before we go our separate ways? Are there any burning questions? Going once, going twice. Okay. If there aren't any burning questions, we're actually going to go ahead and end the session here. And from one beautiful mind to another, enjoy the rest of your day. And we'll meet back on Wednesday. I do want to encourage you to use the pre-recorded lecture to finish this, because more than likely on Wednesday, I'll probably go through homework questions, all right? Since you already have access to that recording. Again, if there aren't any burning questions, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of the day, guys. Take care. Peace. Okay, let me make a copy of this available for you guys. Okay. All right, guys. Enjoy the rest of your day.